Stephen start from here. Thank you, Stephen.
Well, thank you, David, for introducing me, and such a pleasure to come back here to give a seminar. So we are biostatisticians, right? So our job is to test hypothesis, and is to provide evidence of science. Okay, but today I'm giving an example about a further step we can do. Okay, we can build application. Okay, we can create a product. So especially when the hypothesis is not that clear, and when the test is not that clear, so we are able to use our capacity of the knowledge discovery to create a medical application, which is make it very meaningful for medicine, for healthcare. And this is the study was published in Nature Scientific Report in 2003. And it got, this paper got a lot of, attention and good citation. So we got the citation from Nature Review, very high impact, Nature Digital Medicine. And we got from, Advanced Science, with all, high impact for journal. And the Journal of Neuroscience, okay? And also, it has been cited by a large consortium in Europe for MRI in multiple sclerosis, and as a practice guide. And finally, so this made it to the highlight of the largest conference in MS care. We call ATRIM. Okay? It's an international conference. So why it got so much attention, right? About this finding. And let's first talk about what is MS. What is multiple sclerosis? Multiple sclerosis is a neurodegenerative disease. So it comes from the autoimmune attack. And for some reason, the people has this kind of like overreactive autoimmune system start to attack myelin. Myelin is the sheath around the axon, the white matter. The axon. When the autoimmune system attack this sheath, it will break the track. Okay, it creates something called black hole. So when it happens, what happens? Just like when your computer got cut off for the power line and cut off for the cable, what happened? It's dead. So that's what happened, for the multiple sclerosis patient. Okay, it's a highly prevalent in Caucasian compared to other race. So for MS, okay, there is a multiple steps of the disease. So the first phase is called trigger phase. This is preclinical. So at this stage, we have no idea what happened. Okay, it's complete dark. So it having adolescent, okay, and probably some genetic effect there. I know, some of our faculty in the department, Talak, he did some genetic study with neurologists as a multi-ethnic cohort to study the genetic effect or contribution to MS. So this is a period that no one knows. Okay, so it's dark, like it's like a preclinical period, and then they have the actual preclinical period. It's an inflammation period, and in this area it's called radiological isolated symptom. There's no clinical symptom, only exists in the imaging. Okay, only if you do the MRI you can find it. Okay, however, because we don't have anything in MS by using MRI as a routine screening, we can't find it. The only findings, of the RS cases is from those healthy control who come here to get like a research because their sibling has MS, or they come here to get a scan, for like a headache or for other reason, and they accidentally identify it's, those RS patients. So unlike like the mammogram in breast cancer detection, you can have a routine exam. MRI is impossible to get, routine as a screening, for neurodegenerative disease. It's too expensive and too time consuming. We don't have that much resource on that. The next phase is called relapsing and remitting MS. So at that stage, the symptom on and off, usually lasts for 10 to 15 years. So that's the most frequent, that's a typical time that the MS being identified, okay, because they have clinical onset. After that, it's called progressive MS, because the symptom will be persistent and the degeneration will be persistent. Okay, it will go all the way to the end, and so this is the complete out of control, this phase. And you can see the brain volume, drop, atrophy, drop a lot at that phase. So this is an example for the radiological isolated symptom. If by our naked eye, we can see it. It's just those white spots, okay, white the hyper enhanced, the white spots, okay, in the MRI image. Okay, so how do we treat those? Okay, how do we treat those? We have about 20 different treatments for MS. So those treatment is called disease modification therapy, okay, DMT. So what DMT do? Okay, some DMT is very, very aggressive. Okay, just like chemotherapy, it wipe out the autoimmune system. So during the COVID time, okay, we are very, very concerned about the MS patient because they have compromised autoimmune system. The autoimmune system being wiped out by those disease modification therapy. Okay, and also there's some other treatment just to protect the neuron. So there's many different treatments. How to select those? How do we decide what treatment best for the patient? So it will lead to a very important field in the medicine. It's called precision medicine. Precision medicine is determining when and how and what to choose, to give to who, right? And in the field, okay, so in 2022, in the Journal of Neurology, so they have a joint statement, okay, from expert panel about the early treatment, early use of high efficient DMT for MS. So they found the effect size, okay, for the same drug. Okay? The effect size, if you use in the early stage, it's about 5 times stronger than the later stage. So here is a joint statement. Okay, early progression in MS, okay, is characterized by new information and subclinical neurodegeneration that may be underestimated. Okay, by the medical society. So early disease phase are the best window for therapeutic opportunity for MS. Okay, the treatment goal consists in hindering the underlying pathophysiological mechanism, which is the inflammation and the neurodegeneration. So the early in the disease course can prevent the progression of the disability. Now the question is, how early is early? How do we determine it's early? Okay, let's go back to this diagram. Most of the time, when the physician encounter the patient, it's around this 10 to 15 years of period for relapsing and remitting MS. When there is a patient come to you around 40-ish, how do you know the actual onset of the disease? How do you know this patient is in early disease or not? Because why? Because there is a long and unknown preclinical activity there. So the autoimmune system just actively attack the nerve, but without the clinical symptom, right? So that's a $1 million question. Should we treat them or not? Okay, by default, almost all MS patients will get those aggressive DMT. It will induce the autoimmune system to compromise the autoimmune system, to wipe out autoimmune system. This is too aggressive. If it's not necessary, those treatments just introduce a side effect, nothing else but side effect. So if you treat those progressive MS by those aggressive DMP, nothing will help to stop the disease progression because it's at the very end stage of a disease. And now here's our study. Try to figure out how early is early, okay? When should engage the treatment? That's the focus of this study. Okay, so a question for the clinician. So to answer that, to figure out how early is early, the first is when is the biological onset of disease? Because the biological onset is the clock start tickling when the autoimmune system attacking the brain, attacking your central nervous system. When does it happen? Okay, we don't know. Okay, so what's the actual disease duration? Okay, at the treatment prescription. So, like how old is it? Fresh disease or is a disease being there for a long time? It's an old disease. Okay, and so then, is there a range of disease duration indicate the period for effective treatment? Okay, so should we classify patient based on the symptom or the mechanism? Okay, can we guess the biological onset age in the past based on the current data we observed? Okay, now back to our job as a statistician. Do I see any clear hypothesis to test? No. Okay. Do I have any concrete target to do machine learning to predict? No, nothing. So pretty much in the dark, okay? But what we have is some data, some useful data, okay? Not perfect, some useful data. Okay, I will show you how to be creative, okay, when we use this data, how to be creative. I'd like to introduce the concept called digital twin, okay? It's also a very trendy concept, okay? So this concept starts with the Apollo program. So they have two vehicles, one in the space, the other in the station on Earth, okay? So if the space vehicle having problem, they can't fix it, but they can do simulation. They can just transmit the problem back to the base, and people in the base, they will simulate the problem that occurred in the space and then fix it and then just tell people how to fix it, all right? So same thing, okay? So in precision medicine, ideally, we can do what? Can do n=1 trial, okay? You can put patient into different treatment and to figure out what's the best for the patient, but how many treatment you can give to that single patient? Not much, right? How do we do it? Simulate. Nowadays, a digital world, okay, we have so much data. So by using the data, we can actually form the digital entity of the body. We can form the digital entity for the heart, for the tumor. Then we can start the simulation based on the large data we acquired for people who've been the treatment, been through the treatment before. And we can simulate what is the best for the patient. So that's the key for the digital twin in medicine. Okay, so this concept first invention introduced to the manufacturer or the industrial world in the year of 2003. Okay, so the term digital twin officially published in 2012 by NASA and Air Force. Okay, and then around 2010-ish, it has been introduced to the medical field. So after that, oncology, geriatric, cardiology, infectious diseases, many fields, they start use this term. Because why? Because, oh, by the way, see the sign, I think even register the trademark called molecular twin. They even trademark this. Because why? Because in the digital world now, you're able to simulate, use the data to simulate, to create a digital entity of the body and to simulate, okay, to provide inference. Okay. And okay, now let's talk about the how do we create the digital twin? Okay, so of course, to understand what is the biological onset of the disease of the multiple sclerosis, we don't really care about the heart or the kidney, right? All we care is the brain, right? In the brain, which part brain is complicated, okay? Although it's small, it's about like a 3 to 4 pound, but it's complicated, okay? Which area will be most interested to us? Okay, we look at different area of the brain. So again, the goal is to look at the early, right? To look at early. So we want to find the area in the brain can have a very good, this like distinguish the disease from normal at the early time. So we look at data from RIS, the radiological isolated MS, those early stage MS, and we look at the control, and we find out there's a little area in the brain called thalamus. So that's very sensitive to distinguish them. So that's the area we're going to focus on, thalamus. So just like, two pigeon egg, okay, in the brain. Okay, then we do a further study. Okay, we look at the so-called the lesion, the gadolinium. When you put the counter agent in the body, so through the body, you can highlight the lesion. So it's called gadolinium lesion. So we look at the lesion volume and look at the we count the lesion in the different tract, because in the brain, because multiple sclerosis is a white matter disease. White matter disease, you have to look at white matter tract. So look at the lesion on the tract, count how many of them. So by look at this tract, we can look at the proportion of the thalamus volume over the entire white matter volume is about 28%. But look at this, okay, 78% of the lesion volume were found in thalamus tract. So the majority of the lesion, okay, for the white matter damage is in the thalamus tract. So what is the thalamus? The thalamus is more like your the cable switching board. All those cable, the white matter tract, they come to thalamus, they do a switching. It's like a switching station. They communicate. All those cable to communicate through this like a station. It's called thalamus. So this is like a surrogate for the white matter disease. So the density of the lesion in thalamus tract thalamus white matter tract is 10 times higher than the other white matter tract. So this is this. So we pick the thalamus, okay, and now we look at what? Look at thalamus atrophy. Okay, because when this little area being attacked by autoimmune system, it will shrink. Okay, it will shrink. And okay, so then talk about the shrinking, okay? So the shrinking has a pattern, has a trajectory, okay? So what do we believe? Is trajectory is a linear or not linear, or what kind of trajectory? What kind of trajectory format we can think about? Okay, it's important. Why? Because we have to determine what kind of model we're going to use, right? So if it's a linear, we use a linear model. If it's not linear, we have to look at what kind of non-linear pattern we're handling. So this is a landmark study published in 2022-ish, or let me see, 2022, yes, 2022. It's published in the Nature, okay? So this study aggregated over 12,000, okay, MRI scan across 100 primary studies, aggregate from 100 studies, and from over 100,000 human participants. Okay, look at that. Okay, so like this is okay. So this, okay. So like first, okay, look at white matter, gray matter. Okay, so the gray matter, look at from the birth to the adolescent to the adulthood. All right. So of course the brain grow, but the gray matter grow faster than the white matter. The white matter is a little bit delayed, and but the gray matter, go down the hill, like after the adolescent, and the white matter still keep growing until the young adult, until adulthood, and then start, and then start decreasing, and the subcritical volume. So the thalamus is the largest volume in the subcritical, subcortical. Okay, subcortical. Here is our thalamus. Okay. The thalamus, subcortical, it grow, it's about like 18-ish, right? And then start decreasing, okay? Remember that, okay? 18 reach the peak and start decreasing, okay? And then look at other area like the total brain, the whole brain volume, okay? It's increased about the same, the whole brain volume is similar to the thalamus. to the subcortical. And mean cortical thickness, how thick is the gray matter. It go up fast. Oh, David, question?
So really sorry to interrupt, but just going on this statement you made about it decreasing, is it that the different types of matter decreases, or that the percentage decreases because other matter is increasing and growing at a different rate during that?
These are the absolute values, not relative. Yeah, it's absolute right. Okay, it's a relative. Okay, it's relative. Some, when other part of the brain increase, some decreasing. This is very important comment. And in my study, the volume I use is normalized by the total brain. Okay, so that's why we learned this. Okay, it's I normalize by the total brain in my study. Okay, so that is can rule out the confounding about the total brain growing, the total brain grow or shrink.
Okay, thank you.
Is there a point where these dip low and you get to the clinical disease, and which of these, gray matter, white matter, when it gets below 80%, do you start having problems, or?
Okay, again, it's a very important question. Okay, so in human, no, in a healthy population, the was over 18, the atrophy slope, it's about like a 0.2% per year, but that's based on some very rough linear model. Okay, and for the patient, the MS patient, it's about 0.7% per year. Okay, it's also based on a rough linear model. So, and how much loss corresponding to how much of function loss, we don't know yet, because it's very brain region specific. So we have to look at those white matter atrophy, affected region. If it's a motor region, then people are paralyzed, can't move. If it's a speech and lose speech, but it's just like stroke. So it's very hard to figure out. But it's $1 million question. How much is much? How much affect the function? Okay. All right. Okay. Here. Okay. So here again. So like these are the area we interest. Okay. So this is from here to here is the area of interest, and we specifically interest in subcortical volume. Now let's look at our data. Okay. Here's our data. So look, non-linear, right? Clear, not linear. So it's aggregated about 2,000 healthy sample. Okay, so it's not linear. So male, female, not linear. So around 40-ish. So it all start decreasing. The atrophy start, and the female has a delay. Male atrophy faster than female. So that explains why ladies are smarter than men. All right. Now talk about our study rationale. Okay, so the thalamic is one of the earliest affected region in MS. Okay, right? It declined consistently throughout the disease duration, and it would follow a predictable trajectory under the normal circumstance. So when we proceed the study, ask people to do a lot of intense work, we have to have a good rationale to do the segment, to segment out the thalamus through thousands of images. It take about like probably like a couple hours per scan. If we do like a 2,000, that's a lot of hours. So we have to have a good rationale, a good reason for people to do that. All right. So our objective is to establish the onset of disease related something called progressive brain tissue loss. So this is not the clinical onset, it's the onset of disease-related progressive brain tissue loss for MS. So it's very close to the biological onset, but we can't say it is the biological onset, but it's closer. Okay, we should try to look at when the brain tissue start deviated from the normal. Okay. All right, so then, okay, now imagine, okay, so if here is MS patient. Okay, so if this patient has a brain atrophy speed up at like age 25, okay, and you have a reference line, assume if this person can have a second life, without MS. And you can measure another trajectory line, right? So if you look at this, put these two trajectory lines together, you can look at when, at what age the patient trajectory line deviated from the your healthy control. So that is the age when the attack starts. So that is the progressive brain tissue loss age. It's a very important concept. Okay, do you guys follow that? Okay, now, can I have a second life? Can the patient have a second life? No, of course no. What's the second best? Twin. We have a twin study, right? Twin study, ideally, with twin. If you have a twin and no MS, then you can do that, but so rare. So rare to have a twin study with and without MS. What can we do? Digital twin. Right, okay. Well, it's a good dream, right? We have a digital twin, right? So, but what is the reality? Okay, well, the reality, well, that's a dream, right? The Ferrari, but the reality is a Toyota. So what do we have? The data we have. Okay, so we only have a few years of follow-up. So we want to have, remember, so we want to look at the lifespan, okay, the trajectory lifespan, but we only have a few years of follow-up, 3 to 5 year follow-up. And very rare we have a normal control identical twins in MS. That's gone, okay, long gone. So and the worst scenario is for the normal or for the healthy aging group, mostly we only get the cross-sectional data. We don't have longitudinal data. Why bother to have a healthy people to get a repeated MRI? So we're not that crazy, right? So most of the time we only have cross-sectional data, right? But what we expect is we want to have a lifespan MS scan, and we have a matched control with our MS patient, and we have a longitudinal, scan with the normal aging cohort. Okay, so here we have. Okay, so we have that's the best we have, about the new imaging data in the world. Okay, that's the best we can get. Okay, you can't get any better than that. This all comes from a large consortium. So HCP data, we have the D with A and the HCP, and we, for HCP D data, we have 178 subjects, but they all cross-sectional. Only one shot of measurement, and all HCP they're cross-sectional. And UCSF cohort, we have 87 of them. And they have about like 1 or 2, scan. And Annie is another cohort, but it's all senior, very old, okay, very old patient. So they have some, repeated scan, the 2, but no more than 3. Okay, so if you look at the table, okay, what kind of a challenge am I facing? Number one, the age distribution, right? So we don't have enough young patient or young control. But my interest is the younger population because onset is earlier. So you can't look at people 70 years old, talk about the onset of disease, it's too old, game is over. So that's my biggest problem. That's why I think about a Toyota, okay? So, and the second problem we have, okay, look at those scan, the detail of the scan, look at those. Are they the same scanner? No, some from Siemens, some from GE. Are they the same scan protocol? No, they're not. So MR is tricky. So if you not come with the same scanner and not from under the same protocol, the difference could be as high as 10 times. Now you try to combine them. Okay, the problem. Okay, but this is not the scope of this talk. Okay, so we have technique to deal with it. Okay, so the number one technique is to use a relative ratio, as you guys mentioned, to use relative because the signal. If I use relative, the ratio it cancel out, right? It proportionally go up and down, right? This is one strategy. The second strategy is use statistical harmonization, the Bayesian harmonization. Okay, we tested both, and that's a different story. Okay, so this is a group of imaging statisticians just focus on the imaging harmonization. Okay, now the data processing. Okay, so we use free server to do the segmentation. It takes awfully long. Okay, and the normalized forms volume. So we normalize by the ICV intracranial volume. That's the brain. That's the total brain size. Okay. All right. Okay, now, so here, the fishbone, okay. We have the cross-sectional data, but we want the what? Longitudinal data, okay? What can I do? If I don't have, I have what? I have to augment, create something that okay, just like the missing data imputation. When there's missing data, some data missing, we call data missing the imputation. If all data are missing, we have to call it data augmentation because you augment for nothing. So how do we, what is the fundamental, like the philosophy behind that? Okay, so if you look at the nonlinear data, large, high quality cross-sectional, nonlinear data, you can have a population-based trend, right? So it's just like the spine bone of the fish, right? And then the longitudinal data is just like when you grow the rib cage bone, okay? So in a relatively long period of time, like 3 to 4 years, you can assume it's linear, it's not change much, right? So based on this assumption, okay, we can try to grow. So we have a very nice fitted spline model. Okay, based on that, we can use this to try to grow, the rib cage and to augment a longitudinal data. Now I will show you. We did pretty good job. When we do that. So when we have this, we combine with the longitudinal data from MS population, and then we can have a longitudinal data combined to do something fun. Okay. All right. So here. Okay. All right. Okay. So how do we fit this cross-sectional spline model? There's a many way of fitting the spline model. Okay, I choose this one. Okay, the multivariate adaptive regression spline because this is a very powerful method. So this method. How many of you have heard about this method? Probably not. Okay, so this is from Stanford. Okay, talk about the machine learning. Machine learning is UC Berkeley, Stanford, they are pioneer for machine learning. Okay, so stuff from Leo Breiman, Jerry Freeman. This method from Jerry Freeman, stuff from 1991. And so when we talk about spline model, we have different spline, and you guys probably heard about something called the generalized additive model. So this is one of the methods, but this is more powerful than that, okay? Because this is combined. It's a non-parametric regression, but it combines both regression spline and model selection method. It belongs to a machine learning because you don't need to specify the knots, okay? And it will just automatically search for you, okay? And especially, okay, when you have inaction, and you have high dimensional data when you have inaction, you can do like hands-free. It will search for you. Okay, so this is more advanced compared to generalized additive model. But the downside is it can only work on the cross-sectional data. So we don't have any Mars model for longitudinal yet. However, though, even that, I may not choose that method. Why? Because depending on what you're looking for. So if you're looking for an accurately prediction model, you can use the Mars model. But if you want to look at the spline for a specific predictor like age, you probably not want to stay away from that. Because why? Because it will break the bundle of the inaction. You will break the bundle. Okay, it will just aggressively go with prediction and doesn't care what you care, the slope. It will break the slope. Okay, but here our question is simple because our predictor is not a lot, only age, sex, and the brain size. Okay, based on that, okay, we're able to construct a slope, follow the skeleton, follow the pattern of the data. Okay, eyeball is pretty accurate, right? Pretty accurate. Follow the trend, and if you look at, and also we have some longitudinal data. So we have 433 repeated measure. So we hold the second measurement as an independent testing. When we apply the model to the independent testing data, okay, with the withhold second measurement, we can get the correlation coefficient at 0.67 just by these three variables. Okay, it's pretty good. Okay, all right. So now we have the data augmented. Okay, now we have data prepared. Okay, we have the longitudinal data from both healthy aging and the MS patient. Next is the mixed spline. So have you guys used a mixed spline? So it's a mixed, special form of mixed model. Okay, but as a spline. Okay, so let's look at notation. So mu, mu ij is the unspecified aging trajectory. So again, we only care about aging trajectory. Okay, other stuff is accessory. Okay, aging trajectory is a prime. Okay, so mu ijt is the age trajectory spline. So the beta is a regression coefficient for other predictors. Okay, and upsilon is a random effect. We have to deal with random effect. Okay, so mu is, you can consider mu is a fixed effect, and upsilon is a random effect. Okay, with aging of each subject, and the epsilon is the error term for the normal distribution. Okay, with a covariance matrix, we can deal with that. Okay, so it's a semi-parametric regression model. Okay, so with a parsimonious way for both to capture both the potential non-linear age trajectory and investigate the impact from other predictors. So it can be downgraded to a linear model. So if the spline trend doesn't exist, okay, it can automatically downgrade to the linear model. Now let's talk about spline. So how many different spline bases we have so far? So we have, number one, we have a truncated power function. The truncated power function is look at the break, okay, and we have a B spline basis, and we have a nature spline base. Nature spline base is just a constrained spline, okay, constrained spline. I will show you now. Sometimes the constrained spline doesn't work well. The constraint is very arbitrary to force something to the linear, okay. So this model varies by choice of the spline basis and tuning parameter. Tuning parameter is about number of the knots and the knots position. So in statistical field, we don't really talk too much about the tuning parameter, but in the computer science or also data science, they talk about the tuning parameter all the time. Because when the model getting complicated, you really don't know which one is the best for your model. So you have to, try many ways. Okay, so the way of tuning is called grid tuning. Grid tuning means you try all possible combinations, and then you select the best combination for your model. Okay, all right. So we have to tune the parameter to find the best fit. Okay, so so there's two major steps to fit this. Okay, one is to approximate. Okay, to use the basis function. Okay, like truncated power or B spline, which allow to fit low order polynomial with very small interval proportion. Is a base of knots to search. And then we have the smooth. So smooth or penalty is just to prevent overfit. Okay, so this is a fancy term, the penalty. So we do random spline coefficient, topless, G psi matrix is just the random effect. Okay, and or ratio smooth for the G psi matrix. So the smooth could be done, through the generalized cross validation. This is very important term, the cross validation, to minimize the overfit, or just the mixed effect approach. Okay, so then so this model will allow to penalize directly to the model coefficient. It's the similar concept like a lasso. Okay, just look at the beta coefficient, look at the square difference between for the beta coefficient between adjacent model coefficient. Okay, and then we can penalize it. And so the again, then to penalize it, so we downgrade this to or we approximate the penalized spline to two options. Okay, one is called cubic B spline, and also the second is called cubic truncated power function. So how do we do this? Okay, so how do we use cubic spline to penalize it? So this is a notation adopted from Rupert, Ward, and Carroll. Okay, so we have So, xi, is the polynomial function, beta 1, beta 2, beta 3. And the second part, is the truncated power function. So the t is a knot. Okay, t is a knot. Okay, so then we use the cubic spline to for the penalty. And so the goal is to able to, in a longitudinal spline, the goal is to able to repeat this, to repeat the same trend what we observed from large cross-sectional data. And when it's because the spline model is complicated and also very easy to get overfitted. Okay, if you look at the spline, sometimes it dance like crazy. Okay, it's called wiggle. Okay, over wiggle, that means it's too much overfitted. And it's not easy to find what is the best, best fit spline model. I will show you later. Okay. So then, of course, for statistician, we always want to simulate data before we want to play with the model we have. So to simulate the spline model, it's not trivial. Okay, and you have to simulate exactly the same shape. So what we did is to use a piecewise approach. So we have 10 H block from 30 to 80, okay, and we have to mimic the decrease or the trajectory for the intercept and for the slope, okay, for these 10, these 10 H blocks, and we accumulate them together to aggregate this simulated spline. So that's what the simulated spline looks like. Okay, so it's very close to the data we observe. Okay, so we reiterate 500 times, and we have one single data set, the testing data set with 50 sample with whole. Okay, so this 50 sample has age from 26 to 80. Okay, and we hold this data, and we have 500 data. We reiterate the chain. Okay, we apply this one testing model. Okay, and let's see how accurate it is. Okay. Okay, now, we look at AIC, BIC. Okay, we take average and look at model fit. We have 12 different models. Okay, here we compare AIC, BIC. It's very classical, traditional to look at the model fit. And then we have to look at the predicted or estimated Thorne's volume, and we associate 95% confidence interval. And we have 500 replicates, and we just take average, okay, for the estimate and for the confidence interval. And we graph it. We have to graph it. For the spline, we have to graph it. Without graph it, you really can't adjudicate what works best. So here's the AIC. Very clearly, you can see the winner. Okay, topless and cubic B spline is the winner. It's the smallest AIC and BIC. Okay, now look at the graph. Okay, so C and D, what's wrong? C and D, the green is the predicted. Okay, the red curve is the actual simulated curve. So C and D over constraint. I call over constraint. It comes from nature spline over constraint. It almost falls into a linear trend. Okay, bad. Remove it. B, what's wrong with B? Well, although it's kind of follow the estimated or the simulated spline, but the confidence interval go wild. Okay, especially in the earlier age, it go wild. Okay, this is something we don't want it because it's inaccurate. So by observing the pattern, we can also enforce us how to pick this. What is the hyperparameter we want to pick? Okay. So now, before we start applying into real life data, let's repeat again about what's the strategy. Number one, we construct a well-fit spline model in healthy control with question data and use Mars and to find this like the spine bone of the fish, and then we augment this. So we augment the longitudinal data. Okay, we augment 2 observation, younger than the observed age, and the 2 older than observed age. So every subject 5 years of follow-up. Okay, and we feed the mixed spline model. okay, to combine the longitudinal data from the MS and healthy population. And we also fit the 12 spline structure and we compare. We haven't forget that the covariate, we go back to us, right? The covariate. So because this is not like machine learning, we can have an open just for the prediction. Okay, so we particularly interested the trajectory, the slope of the age. We can't just open it up, let the machine tell me. I have to force the machine to look at what is the spline term for the age and what is interaction with a spline. Is there any factor can moderate the spline term? So that's why I have to look at, or we have to look at the covariates as a bundle, as a group, one by one. It's a very tedious way to look. So we have 52 different covariate patterns to deal with. And then validate it, very importantly, by the tenfold cross-validation. So in the statistical practice, we care about the p-value, care about the confidence interval, but in the prediction or the machine learning or prediction framework, we care about what? Care about accuracy, care about the accuracy of the prediction. Then the cross-validation is the key. So you have to use cross-validation. And identify the age onset, okay, define it. And the last one, the number 5 is how you create the product, okay? So your product, or my product, is to define the age of onset of progressive brain tissue loss. So define it as the age which the thalamus volume trajectory on the individual MS patient deviated from their expected control, okay? So the so-called twin is expected at the same brain size, same age, same sex, and the same age, same sex, okay? So we have this, the so-called twin means you match with all those characteristics, okay? We call this twin. So you get expected value, longitudinal value, and then you look at that, and then more of this, the inference comes from the bootstrapping. Because we have no idea what is the confidence interval for the age of progressive brain tissue loss is. You can't just give one number. So how confident you are. So to get the confidence interval, we use bootstrapping. So here's an example about the covariate patterns. So this is like an example of two-way interaction. So you have the H spline, okay, and H spline, and of course you have MS or not. So it's one of the effect modifier, and you have the brain size. So just you exhaustive combination of all two-way interaction. Okay, you feed the model one by one, and then you compare. So then we can have like no interaction, two-way interaction, three-way interaction, all the way up. Okay. Okay, all right. So winner is the B spline with topless covariate structure. Okay, so and we have identified the final feeding, the model, the final model for the feeding, and the final performance after the cross validation, we can have 0.88 of correlation coefficient between predicted and observed data. So that's pretty good. Okay, so these were done by using what something called repeated measure correlation. So when we talk about the Pearson correlations, cross-sectional data, but the repeated measure correlation is done by at the individual level. Look at whether my observation 1 doesn't match with expected 1. My observation 2, predicted 2. So it's a repeated correlation. So 0.88 is pretty good, okay? Graph, back to graph, okay? How we select the best fit? Besides the model feeding index, AIC, BIC, we have to observe the pattern of the trajectory for all the combination. So we have 12 different model, different hyperparameter combination, right? And we have 52 covariate pattern. So that's 12 times 52. That's how many of it we have to observe. So if you look at some of it, too much wiggle, okay? Like this, too much wiggle. This, too much wiggle. Okay, look too much wiggle, okay, it's overfit the model. And some of it is very wide, the confidence interval, too wide, we dump it. So at the end, that's what we pick, okay? So when we the model we pick, the finance model, we apply to the 50 independent testing data. So if you zoom in, okay, if you zoom in, you can see this is the healthy reference line. The yellow is the trajectory for MS. So you can see most of the case, majority of the case, the predicted line for MS are crossed through the observed data, observed value. This is pretty amazing. Okay, it's smart enough to cross through it. Smart enough to cross through it. Okay, so this is about. I will show you two examples. Two patients. Okay, the patient number one has the clinical onset age at 39, and this patient come to the study around 40. Okay, so the second patient also come to study around age 40, right? First observation around 40. And this patient has the clinical onset at age 25, okay? Look at these two. The green dots is the progressed brain tissue loss onset age predict from the model. And then we have the confidence interval. The red dots is what? Is the clinical onset age. Okay. The right side, the red dot is within the confidence interval for the predicted, for the progressive brain tissue loss. And the left side is outside of it, right? So we call the right side as a simultaneous onset. The clinical onset and the progressive brain tissue onset happen at the same time. And the left side is outside of it. We call it earlier progressive brain tissue onset, earlier biological onset, or we can call late clinical onset. Okay, and we plot all of it in this graph. Okay, so well, it looks like a boot. Okay, so do you know why you have a boot? At the end, because this is younger age. We don't have enough sample for younger age. Then we create a large confidence interval. It's indeterminate. Okay, we can't determine it. So for now, if we can't determine it, we just call them, simultaneous onset. Okay, because we can't determine. They have too wide of confidence interval. So the confidence interval is narrow enough, and we can determine. So the either clinical onset is earlier or not, and we create the simultaneous onset and early onset. Okay, if you look at this, okay, so we plot this histogram. It's a very classical way, we like. So if you look at that, so the bimodal, it's a bimodal distribution. It's common two different distribution, right? There are two lumps there, this different distribution. If you look at the trajectory of percent farmer's volume, look at this slope. Slope are different, right? So it's a very different population. Now let's look at the demographic. Again, they are very different. Okay, so here is more importantly, we look at the function data. Okay, look at function data. So this function data, you can see the different MSFC is a global disability measurement for MS. Look at that, very different trajectory of different pattern. Okay. Oh, David, question?
Well, sorry to interrupt, Stephen, but I just want to remind you that we end in about 3 minutes, and there is a class that starts. So we just need to. Okay, thank you very much. Okay, perfect.
Yeah, almost. All right. So look at those patterns. Okay, they are very different. Okay, this is a different cohort. So what next? So next cohort, is what is doing something called in silico trial. So we have a biomarker now. So we try to use biomarker to guide the treatment. So we have two cohorts, UCSF cohort, and we have another one from Cleveland Clinic. So two cohort, large cohort to do the in silico trial. We use biomarker to look at to how to decide to guide the treatment triaging, treatment decision. All right, so acknowledgement is come from R1, and here's the neurology team, and here's my friend and Logita from MUSC. So you guys, many years later, we have this, same have work together, create something interesting in the future. So be nice to your friend, okay? Okay, thank you and have a good Thanksgiving.
Thank you very much, Stephen. Are there any
All right.
questions?
Questions? Do I lost you?
If so, those in the audience, please pick up.
Yeah, hold on, there's one question, yeah.
So like, I'm curious about the tuning part, like, you know, how do you decide what model is the best? Because do you just eyeball it?
Yeah, well, okay, so, okay, couple of things, right? Number one is the AIC-BIC. Number two is the cross-validation performance. You look at your predicted value to the observed value to look at how good they are through the cross-validation. The third is through the eyeballing the pattern. Okay, there's 3 ways to look at that. Okay, the David question?
Well, following up on that though, it seems like the eyeball test that you used was really to incorporate the variance of the prediction, the confidence intervals around that. So,
right.
because often cross-validation uses something that would be the expectation of the curve versus the data, but you really use sort of the confidence interval to say, well, we want it to be tight in this age group and maybe larger there.
Right. The second thing is I look at the wiggle. So because of the whole thing is based on the cross-sectional pattern, right? So we have a large population-based data from the cross-sectional analysis. We want the longitudinal trend follow the same pattern as the one I believe, or one I observed through the cross-sectional, large cross-sectional data. So that's true, I have to look at the wiggle, the degree of wiggle, and also the confidence interval, 2 things.
All right. Well, thank you very much, Stephen. We need to go to let the other people come in. But thank you very much. And if if anybody else has questions, please meet Stephen in the hall. All right.
Okay. All right.
Thank you all. Okay. Bye, Stephen. Thank you.
Yeah, right. Thanks, Rooney.
No problem.